Hello, everyone. How are you guys doing today? Good. I'm doing fine, thank you. So our second exam will be next week, Monday. I posted the review sheet. The review sheet homework due date is tomorrow midnight. I'll post the solution after Friday midnight. Okay. Any question before we start? Any comments? Concern? Brendan?
Is this not the other?
It will not be on the test. It will be the final exam. So today we're going to start chapter 4. Shivu?
Will our final exam be cumulative?
Cumulative. From 1.1 to whatever we're going to cover. We actually have only 4 sections left. 4.1, 4.2, 5.1, and 6.1. Something like that. 4 sections. And we still have 7 classes. Let's see. Come on, I hit that hard, it doesn't work. So 1, 2, 3, 4, 5, 6, 7. 7 classes left. So with our with my 7 o'clock class, we decided to have a day off on Wednesday after your exam. Because Thursday is Thanksgiving. So Wednesday people have lots of things to do at home or do shopping and everything. So there will be no class next week, Wednesday. And we will not be left behind because we only have 4 sections left and we have many days to cover. Okay?
Will there be a review session before the final exam?
So if we cover 4 sections in 4 days, we still have 2 days in our hands. We can do review. Yes. Our final exam will be 16th. Our last day of class is 15. Final exam will be 16. All right, that's 16. 17. Our final exam will be 17 from 5:20 to 7:20. 5:20 p.m. to 7:20 p.m. December 17. Good question. December 17, Wednesday. Our last day of class is Monday, which is 15. And we have 16 Tuesday. Final exam starts from 16. And our final exam will be on 17th. Okay, chapter 4. Chapter 4 talks about linear transformations. So in the study of vector spaces, the most important types of mappings are linear transformations. A linear transformation is a function between 2 vector spaces that preserves the addition and scalar multiplication. In simpler words, it means a linear transformation is a rule that takes a vector, does something to it, like it rotates, stretch, reflects, compress, these things, and gives a new vector without breaking the algebra of vectors. The formal definition of all these informal definition is that a mapping L from a vector space V to another vector space W is a linear transformation if for all the vectors in V and for any scalar, L of the scalar times the vector plus another scalar times the vector is same as the scalar times L of the vector 1 plus second scalar times the L of the vector 2. So basically you can think L as a function of F. So here we are using L because it's a linear transformation. But this one is same as F of A times V1 plus V times V2 is A times F of V1 plus B times F of V2. In other words, a transformation is a linear transformation. If you multiply all the x value with constant, you get the constant times the y value. And if you add two x values, like in function format, if you add two x values and put it into the function, this is same as sum of the y values. So here L like function f and v and w, they are like x values. So they are saying if L of linear transformation of C times vector v is C times, if you put the linear transformation only on the vector v. And if we add two vector spaces and put the linear transformation on the sum, it's same as the sum of individual transformation. If these two things are true, then a transformation is a linear transformation. And if you combine these two, you get the same thing here. So the two operations are applied together here. And if you don't like the two applications together, then you can break them down into two pieces. So linear transformation behaves nicely, like they do not bend, they do not break, they do not shift the entire space. Instead, they stretch, they shrink, they reflect, they lean, they project one onto another, project onto one line or on a plane. So these are a few examples of the linear transformation. What linear transformation will not be is if you add a constant and if you multiply vector spaces, then they are not linear transformation. They're something else. For example, you may apply the linear transformation from R2 to R. So R2 is the XY plane, and R means it's the number line. So you're transforming a point into the number line. So the point from the plane, it transformed into just a constant. This is a linear transformation. So we can transform one plane to another plane. We can transform from R2 to R3, R3 to R2. We can transform from R2 to R or R2 to R2. Like we can transform anything from one plane to another plane. What transformation does is it just changes the output. You are putting inside one thing and it's spitting out another format of another plane. So you may input a point into the function, and then the function does something inside, and it spits out just a number on the number line. So if you do that, it's a linear transformation.
If it starts out in R2, how come it's not a vector? How come it's not a,
It could be a vector, it could be a point. Remember, vector is a point with a direction. So you can take this point or you can take this vector, whatever, and then if you put transformation on it, you can turn this into just a constant on the number line. So you're changing from a point or a vector to just a number. We can do that with linear transformation, and we can do vice versa. We can take a number and then we can transform that into a vector. Now, geometrically or visually, what is happening? To watch that, to understand that, let's watch a fun video. Come on. Move.
Hey everyone! If I had to choose just one topic that makes all of the others in linear algebra start to click, and which too often goes unlearned the first time a student takes linear algebra, it would be this one: the idea of a linear transformation and its relation to matrices. For this video, I'm just going to focus on what these transformations look like in the case of 2 dimensions, and how they relate to the idea of matrix vector multiplication. In particular, I want to show you a way to think about matrix vector multiplication that doesn't rely on memorization. To start, let's just parse this term, linear transformation. Transformation is essentially a fancy word for function. It's something that takes in inputs and spits out an output for each one. Specifically, in the context of linear algebra, we like to think about transformations that take in some vector and spit out another vector. So why use the word transformation instead of function if they mean the same thing? Well, it's to be suggestive of a certain way to visualize this input-output relation. You see, a great way to understand functions of vectors is to use movement. If a transformation takes some input vector to some output vector, we imagine that input vector moving over to the output vector. Then to understand the transformation as a whole, we might imagine watching every possible input vector move over to its corresponding output vector. It gets really crowded to think about all of the vectors all at once, each one as an arrow. So, as I mentioned last video, a nice trick is to conceptualize each vector not as an arrow, but as a single point, the point where its tip sits. That way, to think about a transformation taking every possible input vector to some output vector, we watch every point in space moving to some other point. In the case of transformations in 2 dimensions, to get a better feel for the whole shape of the transformation, I like to do this with all of the points on an infinite grid. I also sometimes like to keep a copy of the grid in the background, just to help keep track of where everything ends up relative to where it starts. The effect for various transformations moving around all of the points in space is, you've got to admit, beautiful. It gives the feeling of squishing and morphing space itself. As you can imagine, though, arbitrary transformations can look pretty complicated. But luckily, linear algebra limits itself to a special type of transformation, ones that are easier to understand, called linear transformations. Visually speaking, a transformation is linear if it has 2 properties. All lines must remain lines without getting curved, and the origin must remain fixed in place. For example, this right here would not be a linear transformation, since the lines get all curvy. And this one right here, although it keeps the line straight, is not a linear transformation, because it moves the origin. This one here fixes the origin, and it might look like it keeps lines straight, but that's just because I'm only showing the horizontal and vertical grid lines. When you see what it does to a diagonal line, it becomes clear that it's not at all linear, since it turns that line all curvy. In general, you should think of linear transformations as keeping grid lines parallel and evenly spaced. Some linear transformations are simple to think about, like rotations about the origin. Others are a little trickier to describe with words. So how do you think you could describe these transformations numerically? If you were, say, programming some animations to make a video teaching the topic, what formula do you give the computer so that if you give it the coordinates of a vector, it can give you the coordinates of where that vector lands? It turns out that you only need to record where the 2 basis vectors, I hat and j hat, each land, and everything else will follow from that. For example, consider the vector v with coordinates -1, 2, meaning that it equals -1 times I hat plus 2 times j hat. If we play some transformation and follow where all 3 of these vectors go, the property that grid lines remain parallel and evenly spaced has a really important consequence. The place where v lands will be -1 times the vector where I hat landed, plus 2 times the vector where j hat landed. In other words, it started off as a certain linear combination of I hat and j hat, and it ends up as that same linear combination of where those 2 vectors landed. This means you can deduce where v must go based only on where I hat and j hat each land. This is why I like keeping a copy of the original grid in the background. For the transformation shown here, we can read off that I hat lands on the coordinates 1, -2, and j hat lands on the x-axis over at the coordinates 3, 0. This means that the vector represented by -1 I hat plus 2 times j hat ends up at -1 times the vector 1, -2, plus 2 times the vector 3, 0. Adding that all together, you can deduce that it has to land on the vector 5, 2. This is a good point to pause and ponder, because it's pretty important. Now, given that I'm actually showing you the full transformation, you could have just looked to see that V has the coordinates 5, 2. But the cool part here is that this gives us a technique to deduce where any vectors land so long as we have a record of where I hat and j hat each land, without needing to watch the transformation itself. Write the vector with more general coordinates, x and y, and it will land on x times the vector where I hat lands, 1, negative 2, plus y times the vector where j hat lands, 3, 0. Carrying out that sum, you see that it lands at 1x plus 3y, negative 2x plus 0y. I give you any vector, and you can tell me where that vector lands using this formula. What all of this is saying is that a two-dimensional linear transformation is completely described by just 4 numbers, the 2 coordinates for where I hat lands and the 2 coordinates for where j hat lands. Isn't that cool? It's common to package these coordinates into a 2x2 grid of numbers called a 2x2 matrix, where you can interpret the columns as the 2 special vectors where I hat and j hat each land. If you're given a 2x2 matrix describing a linear transformation and some specific vector, and you want to know where that linear transformation takes that vector, you can take the coordinates of the vector, multiply them by the corresponding columns of the matrix, then add together what you get. This corresponds with the idea of adding the scaled versions of our new basis vectors. Let's see what this looks like in the most general case, where your matrix has entries A, B, C, D. And remember, this matrix is just a way of packaging the information needed to describe a linear transformation. Always remember to interpret that first column, AC, as the place where the first basis vector lands, and that second column, BD, as the place where the second basis vector lands. When we apply this transformation to some vector xy, what do you get? Well, it'll be x times AC plus y times BD. Putting this together, you get a vector AX plus BY, CX plus DY. You could even define this as matrix vector multiplication when you put the matrix on the left of the vector like it's a function. Then, you could make high schoolers memorize this without showing them the crucial part that makes it feel intuitive. But isn't it more fun to think about these columns as the transformed versions of your basis vectors, and to think about the result as the appropriate linear combination of those vectors? Let's practice describing a few linear transformations with matrices. For example, if we rotate all of space 90 degrees counterclockwise, then I hat lands on the coordinates 0, 1. And j hat lands on the coordinates negative 1, 0. So the matrix we end up with has columns 0, 1, negative 1, 0. To figure out what happens to any vector after a 90-degree rotation, you could just multiply its coordinates by this matrix. Here's a fun transformation with a special name, called a SHEAR. In it, I hat remains fixed, so the first column of the matrix is 1, 0. But j hat moves over to the coordinates 1, 1, which become the second column of the matrix. And at the risk of being redundant here, figuring out how a SHEAR transforms a given vector comes down to multiplying this matrix by that vector. Let's say we want to go the other way around, starting with a matrix, say with columns 1, 2, and 3, 1, and we want to deduce what its transformation looks like. Pause and take a moment to see if you can imagine it. One way to do this is to first move I hat to 1, 2, then move j hat to 3, 1, always moving the rest of space in such a way that keeps grid lines parallel and evenly spaced. If the vectors that I hat and j hat land on are linearly dependent, which, if you recall from last video, means that one is a scaled version of the other, it means that the linear transformation squishes all of 2D space onto the line where those two vectors sit, also known as the one-dimensional span of those two linearly dependent vectors. To sum up, linear transformations are a way to move around space such that grid lines remain parallel and evenly spaced, and such that the origin remains fixed. Delightfully, these transformations can be described using only a handful of numbers, the coordinates of where each basis vector lands. Matrices give us a language to describe these transformations, where the columns represent those coordinates, and matrix vector multiplication is just a way to compute what that transformation does to a given vector. The important takeaway here is that every time you see a matrix, you can interpret it as a certain transformation of space. Once you really digest this idea, you're in a great position to understand linear algebra deeply. Almost all of the topics coming up, from matrix multiplication to determinants, change of basis, eigenvalues, all of these will become easier to understand once you start thinking about matrices as transformations of space. Most immediately, in the next video, I'll be talking about multiplying two matrices together. See you then!
Okay. So now I have some idea about the transformation, what linear transformation means, or what it does on the vector space. Okay, now about the notation. What do you use to represent the transformation? We have two names. One is linear operator and one is linear transformation. So the way we write them is we write L and then colon and then two vector spaces from one, it's going to the other space. So with the arrow, it's telling us what is your input and where it's going for the output. So we write a mapping L from a vector space V to another vector space W is L colon B arrow W. Means we are transforming V into W using a linear transformation. Now, linear operator is when you transform something on the same plane. You do not change your dimension. If you're on the same plane and you're applying linear transformation, then that linear transformation is called linear operator on your vector space V. For example, if you want to do a linear operator on R2, means you are transforming something from R2 onto R2. One example is L of x equals 3x. Why it's a linear transformation or linear operator? It's because you can think L of x equals 3x as it's 3 times y equals x line. If your y equals x vector, you multiply, you make it 3 times longer, you get y equals 3x. That L of x, you can think of it as y equals 3x. Now it's a linear transformation. You can prove that by showing that the two characteristics we need to check, both of them satisfied here. First condition is that if you multiply the x value with some constant and then you do a transformation, the result should be the constant times the transformation of the vector. So if you do L of x is 3x, L of cx is 3 times the cx, the x in the original function turns into cx. Then you can move the c out and move the p inside. So you get 3x inside the parentheses, and c is a multiplicator. So we get c times L of x because the p of x is the L of x. So first condition satisfied, L of cx is c times L of x. The second condition says take two vectors, x and y, add them, and then see if the result is the transformation, sum of the transformation. So you take the sum of x plus y, and then you replace x into L of x with x plus y, you see the 3, but then if you look at them individually, you see it's L of x, it is L of y. So L of the sum of the vectors is sum of their transformation. Our second condition satisfied. So L of x is 3x is a linear operator. Basically, it means we are transforming L of y equals x into y equals 3x on the same plane, xy plane. Geometrically, this is what it means. We are stretching, we are making longer L of x 3 times. Or stretching, yeah. And now let's do an example. Let's say we have So this transpose, it means we are writing it horizontally, but actually it's a vector vertically. So we have L of X as negative X1 and X2. What does that mean? It means our original points are X1, X2. We are transforming it into negative X1, positive X2. So this transformation we just did, is it a linear transformation or not? This is what you're going to prove. Now, we start with multiplying a constant. So L of Cx, it means every x we see in our function, we're going to multiply that by c. So we get negative cx1 and then positive cx2. This is L of Cx, but we can pull out our c as a common factor. So we get c times negative x1 and positive x2. But if you observe, this is actually L of x. So we get c times L of x. So we started with L of c of x, and we get the result c times L of x. So first condition satisfied. Second condition says take the sum of the vectors, sum of any two vectors, and then apply the transformation. If the result is the sum of the transformation, then we are fine. So let's see two vectors, L of x and y. That means every x you see in your L of x, we're going to replace them with x plus y. So we have negative x1 plus y1, and then positive x2 plus y2. So this x1 in the original L of x turns into negative x1 plus y1. The second x2 in L of x turns into x2 plus y2. So what happens then? We can distribute the negative, we get negative x1, negative y1, and then we have x2 plus y2. But then we can separate them. We can say, well, this is negative x1, positive x2. Oops, I don't have space, so I'll do it on the other page. We can say this is negative x1, positive x2 vector plus the negative y1 and positive y2 vectors. Because when we add vectors, we just add them element-wise. But if you observe, this thing here is L of x, and this thing here is L of y. And we have the plus in between them. So we found that if you add the two vectors, the result is sum of their transformation. So our second condition is satisfied. That means if you do this type of transformation, it's a linear transformation. Now, geometrically, what does it mean? If you look at XY plane, the first point, so x1, x2, let's say we have x1, x2 is somewhere here, x1, x2. Okay, this is our x1, x2. They both are positive. Now, the transformation did x1 into negative x1. So negative x1 is somewhere here and positive x2. So it got here. This is negative x1, but positive x2. So what this transformation did to the original vector, what type of transformation you see here? Do you see anything?
Reflection.
It's a reflection. It's a reflection about y-axis. Okay. Any question? Okay, then let me flip pages. Geometric interpretation, the detail says, think this transformation as negative x positive y. It's the point. So we transformed positive x positive y into negative x positive y, and then observe that it's a reflection about y-axis. In other words, here y-axis means x2 axis. The next question. We are transforming x1, x2 into negative x2, positive x1. You can think of it at a point, let's say 1, 2 is going to negative 2, positive 1. This is what the transformation is doing. It's changing x value into y value and y value into negative x value. So if you have x value 1, y value 2, the transformation is negative 2, positive 1. So if you do this type of transformation, is it a linear transformation or not? So what do you do? How do you prove that, whether it's a linear or not? We start by doing what? If C of x gives us negative C, if L of Cx gives us C times L of x or not. So every x you see will turn into Cx. So negative x2 will turn into negative Cx2, and positive x1 will turn into positive Cx1. So you're changing x into Cx, and then you're observing what is happening. They both have C, so we can pull out C as a common factor. And we get negative x2 positive x1. But negative x2 positive x1 is our L of x. So L of C of x is same as C times L of x. The first condition satisfied. The constant multiplication didn't change anything. And then what do you check next? Which criteria or which condition? If you take the sum of the vectors, do you get the sum of the transformation? So every x you see turn into x plus y. So we get negative x2 plus y2. Oops. Because this is our first element, negative x2. So the x2 turns into x2 plus y2. Our second element is x1. So it will turn into x1 plus y1. Again, we can distribute the negative. So we get negative x2, negative y2, x1 plus y1. But again, you can say, well, this is same as sum of the vectors. So negative x1 positive x2 vector, sorry, negative x2, 1. Negative x2 positive x1 vector plus negative y2 positive y1 vector. because vector sum means you're summing them in the element wise. But this is L of x and this is L of y. So our second condition satisfied. That means this type of transformation is a linear transformation. Now geometrically, what is happening? Let's say you're taking point 1, 2. So 1, 2 here. This vector, it transforms into -2, 1. So -2, +1 here. This see the red one is the transformation. And the black one is the original one. So which type of transformation we have this time? Any idea? It's a counterclockwise 90-degree. It's a 90-degree counterclockwise rotation. The black one went clockwise 90-degree, and then it reflects on the other plane. I mean, the other side of the plane. So it's a linear transformation.
So that geometric transformation can only be known by looking at it visually.
I think so. Like when you look at them, you can see.
Okay, because Maisha won't be able to see the geometric.
That's true. Maybe she can visualize, like if you have point 1, 2 on the first quadrant, and it turns into -2, 1 on the second quadrant. I mean, we can see it's 90-degree, but if you don't see, how can you see? How can you understand? Any idea from anyone? If you can't see it, then how do you know?
I feel like the previous one, you could kind of tell because it's just, the top value is negative, right?
Mm-hmm.
So that,
So our x is same, our y is so y is same, x is just changing. Well, same y, but different sign for the x. It means it's from first quadrant to the second quadrant, and we have the same distance from the y-axis. Right. So it's just a reflection about y-axis. It's easy to see. But here in the second example, we know it's 90-degree angle because we can see the distance between the distance between the black one and the red one, the transform one and the original one. But for her, let me see, do I have an explanation here? L has the effect of rotating each vector in R2 by 90-degree. No. In the book, it didn't mention anything. It's a good question. I should think about it. I'll search about it. Now the last one about linear operator. Thank you. We have L of x as the distance formula. Square root of x1 square plus x2 square. Be careful, be careful.
Yep, you got it.
Now, is this a linear transformation? Let's see. We have L of Cx. That means we are replacing every x1 and x2 with Cx. So cx1 square plus cx2 square under the square root. And then what can we do? We have square root of cx whole thing square plus cx2 whole thing square. So what do you do from here? How can you move forward? Any idea? So c square x1 square plus c square x2 square under the square root. Both of the terms, they have c square, so we can pull it out as a common factor. We get c square times x1 square plus x2 square under the square root. And then we can split our radicals. C square under one radical. I don't need the parentheses anymore. X1 square plus x2 square into another radical. So what do you get? What is square root of c square? Is this true for any c, or it's true for only positive c or negative c, or only for 0? Which one? Maisha? Let's see. So square root of c square is same as square root of c whole thing square. They should be same, okay? Now, if our c is a negative number, okay? Let's say -1. So square root of -1 whole thing square. What is square root of -1? I. So we have I square. What is I square? -1. Now what do we have here? Square root of -1 square. So we're going to do the -1 square first because this is inside. We get +1. What is square root of +1? 1. So one of the format is saying the answer is 1. The other format is saying the answer is -1. So do you get the same result for any C? For what type of C, the result will be same regardless of which method you use. Either you apply the square first or you apply the root first. It doesn't matter. Maisha. Good. That's the trick. This is true only for positive or 0. So that's why we indicate that using an absolute value. Means the C you're working with, it has to be strictly positive. 0 is included because 0 is both positive and negative. So the condition says the result has to be same regardless of your choice of the C. Means it doesn't matter whether you choose positive C or negative C. The answer L of C of X has to be C times L of X. Do you have this result? We do not. What we got? We got L of C of X is strictly positive C and then L of X. But we cannot do that because we have to be, our result have to be general for any C. So this condition failed. So this is not a linear transformation. And since it's not a linear transformation, we don't care about this geometric output. What is happening? It was a tricky one. Any questions so far? So we did 3 examples on linear operator. Linear operator means you're doing the transformation on the same plane. Now next, we're going to do linear transformation.
Is it the last one from R2 to a scalar?
Not really, because we still have this thing. What we started, actually it sounds like scalar because the distance is a number, not a vector.
I,
Hmm?
um,
So we have a vector here. So they're saying take this square and take that square. So this is what we get. So it's a vector, but what's the result of a vector? It's a scalar. It's the distance between the 2 points. But it was in the book on linear operator. So probably they are not looking at the distance as a number, they're looking at the vector itself, how the vector is transforming. Yeah. Now the next one is same thing. We are going to prove the same thing, but we are going to change our field. We are going to go from one vector space to another vector space. If you transform from one vector space to another vector space, we call them transformation, not the operator. But we do the same thing, okay? So we are going to prove both of them. L of C times vector is C times L of V. And if you add 2 vectors and apply the transformation, the result should be the sum of the transformation for any vectors in a vector space. But again, just like pivot points, we have different ideas from different people. Some people say, well, we want to be more specific. So they're saying, like subspace, we have to have 0. So if you apply the transformation on the 0 vector on V, we have to get the 0 vector in W. So 0 vector will be the same. And then the 2 conditions we have, they have to be satisfied. And then the last one, if you apply the transformation into negative V, it has to be negative of the transformation. So the transformation has to be a reflection. Okay? So they believe this should be requirement to be a linear transformation. So whatever we have on the left page, we have the same thing on the right page, just 2 more extra things then require more. But I don't care about the right page. As long as you show this, we are happy. Now, interesting examples. We are transforming from R3 to R2. It means we are taking 3 elements and squeezing them into 2 elements. If you do this type of transformation, and in this transformation, we are, so in R2, we have x1, x2. And in R3, so let me write it here. In R3, we have x1, x2, x3. And in R2, we have x1, x2. These are the normal 3 elements we have in our vector spaces. Now, what this transformation is doing is saying, well, I'm going to make x3 as x1. And then I'm going to combine x1 and x2 and make it as the sum for the x2 in the R2 space. So they're taking 3 elements, changing, sorry, x3, not R1, x3. They are making x3 value into x1 value in R1, R2, and then x1 and x2, they're adding them and putting it as x2 in R2. So they're squeezing 3 numbers into 2 numbers. Now we have to prove whether it's a linear transformation or not. Okay. So we have to prove whether L of Cx will give us C times L of X. So L of Cx, it means whatever we have, x3, x1 plus x2. The first one will be C times x3. The second one will be C times x1 plus x2. So multiplying each element in our transformation by constant, and we can pull the C out because they both have C in common. We get C times x3 and x1 plus x2. But this is same as C times L of x. Because this is our L of x. So L of C of x turn into C times L of x. So constant multiplication satisfied. Now we have to check their sum. So we take L of x plus y. That means our first x3 turn into x3 plus y3. And the x1 plus x2 turns into x1 plus y1 plus x2 plus y2. So this x3 becomes their sum, this x1 becomes sum, and this x2 becomes the sum. Every x element you see, you're going to write them as the sum. And then we can switch them around. X3 plus y3, we can write x1 plus x2. When you add, the order doesn't matter. Y1 plus y2. If we move them, we can write them, we can break them into two pieces. In one piece, we get x3. In another piece, is x1 plus x2. This is our first vector. And we are adding the second vector, y3, and then y1 plus y2. But if you look at them individually, the first one is L of x, and second one is L of y. So we found L of x plus y is same as L of x plus L of y. So second condition satisfied. So yep, this transformation is a linear transformation. We squeeze 3D plane into 2D plane.
Wait to be asking this. But the T, when you have.
T means transpose. So if you
T
have
transpose.
1, 2, T, it means this is not a row vector, it's actually a column vector.
Okay.
People write T so that they can save space. I think in the
I just
book,
got confused whether it was actually referred to transformation.
no,
Okay.
it's transpose. Any other question from anyone? Okay, try the next one. I mean, here. Now I have more. Come on. Are you guys done copying? Okay. Try this one. Let me write it vertically so that you can understand better. The first element is 1 plus x1, and the second element is x2. So it's the same thing. You're moving from x3 to x2. Sorry, R3 to R2. So you have x1, x2, and our x3 is strictly number 1. You are transforming this into 1 plus x1 into x2. Is this transformation a linear transformation? Try this and let me take your attendance. Today is 11 what? 11, 19. Thank you. Brandon C, Joseph, Justin, Joseph, no one, please. Gibran, Shibu here, Michelle, Jack, absent, Ashif, absent, Darius, absent, Winston, here, Abigail, absent, Shane, absent, Emily, here, Kanar, absent, Christine, absent, Edison, here, Maisha, here, Brendan, here, Elvin, here, Shafal, absent, Alexander, here, Shitila, here, Wenchuan, here, and Kailun, absent. Okay, any idea? Shibu,
But this wasn't in,
why not?
is it trying to make others feel that,
Mm-hmm.
the 1 plus 3x1,
1 plus CX1,
yeah,
CX2.
have to bring out the C,
Mm-hmm.
but then I gave them C. The 1 over C plus x.
1 over C plus X1 and X2. Which is not same as C plus 1 plus X1 and X2. So it fills the constant multiplication. It also fills the addition. As long as it fills one thing, it fills the entire thing.
The 0 vector.
0 is not here because 1 plus 0 is 1, not 0. True. It's not a linear transformation. So here in this example, I have the sum. If you take the sum, you get 1 plus x1 plus y2. Sorry, x1 plus y1. And then x2 plus y2. But then they are not sum of L of x1 and L of x2. Sorry, L of x and L of y. So sum fill, constant fill, 0 fill, everything fill. How about the other way around? You are turning R2 into R3. So you have point x1, x2. You are transforming this into x1, x2, and 1 as the third element in your R3. If you transform this way, is it a linear transformation? Basically, it's asking the transformation we did from R2 to R3 or R3 to R2, do both of them fill, or it's only one way filling? What do you think? Is it a linear transformation or not a linear transformation? Idea? Alexander? Why not? It's 0 is not here. Also, the constant multiplication fill, the addition also fill. You just have to show one of them. So you can work with the constant multiplication. CX1, CX2, and 1. We cannot multiply 1 by C because we are only changing X into CX. 1 is not an X, so we cannot multiply that by C. That means we cannot pull out C as a common factor. If you do, you get X1, X2, and 1 over C. So 1 over C is not L of X. This is not C times L of X. So it fails. How about the next one? We are doing operator, means on the same plane. Any square matrix. If you multiply any square matrix by 2, is it a linear transformation? So n by n, it means a square matrix, the space with all the square matrix. So what do you think? Is it a linear transformation? It's not a linear transformation. Any idea from anyone? Alvin, what do you think? So we need to prove that. Which is C times L of X. So first condition satisfied. How about the addition? L of B. Second condition satisfied. So yep, it is a transformation. Because you're not changing anything here. You're just multiplying by 2, so making it bigger. That's it.
Wouldn't 2 times AC be 2C times?
In multiplication, the order doesn't matter. So you're talking about this one, right?
Yeah.
So I can write 2 times CA. And then I can pull out C, bring that 2 down, 2 inside. So C times 2A. In multiplication, C and 2, they both are scalar. The scalar multiplication doesn't follow the order, doesn't care about the order. In the matrix multiplication, order matters. But C is a scalar, not matrix. With this, we are done with the main idea of 4.1. And now there's a concept. I'm not going to go over in details. I would just like to show you a video for you to understand this. But this will not be in the exam. Okay. Kernel, the word kernel, does it ring any bell? Does it ring any bell in your head? Did I talk about kernel before? You don't remember? Elvin, why did I talk about kernel? Good job. Kernel is a null space.
Oh,
When I talked about null space, I said null space is represented by n of A or null of A or kernel of A, all these things. So it's basically null of A, meaning the solution space for the homogeneous system of equations, and image is like the domain, range, those things. So basically one of them is domain, one of them is range. So if you take linear algebra, then this will be helpful. Otherwise here, we don't care much.
This is your brain when you're struggling to focus. And this is your brain when you're in the zone. But getting in...
Professor Dave again. Let's talk image and kernel.
He knows a lot about all kinds of stuff. Professor Dave explains.
Now that we have learned about linear transformations, we have to discuss 2 related concepts, and these are called image and kernel. These are best defined by example, so let's take a look at one now. Say we have a linear transformation that maps from the vector space V to the vector space W. As we know, this will involve taking vectors from V and turning them into vectors in W. If we transform a group of vectors from V, we end up starting to map out several vectors in W. This is the idea behind what we mean by image. If we take a subspace of V, let's call it S, this is a group of vectors from V that can then be transformed. The set of vectors that we can get from this transformation is what is known as the image of S. One way to think of it is that it's as if we are shining a light on a part of the vector space V and seeing how much of W gets lit up. The area of W that gets lit up is our image. The image of the entire vector space V, denoted this way, has a special name. It is called the range of L. For example, consider the linear transformation that maps R3 to R2, given by L of V equals V1, V2 minus V3, for any vector in R3. For this example, let's say our subspace of V is given by the vectors of length 3, where the second element is 2 times the first element, and the third element is 0. Written out, this is the set of vectors of the form C, 2C, 0, where C is any scalar. Let's plug this form into our linear transformation and see what we get. Our transformation says to plug the first element into the top row, so C. Then plug the difference of the second and third element into the bottom row, so 2C minus 0. We end up getting an image of the form C, 2C. The image of our subspace is the set of vectors of length 2, where the second element is twice the first. Now let's move on to kernel. Keeping in mind the fact that our linear transformation maps from V to W, the kernel of L, denoted as shown, is the set of vectors in V that, when transformed, become the 0 vector in W. To keep 0 vectors distinct, we will write the 0 vector from V as 0 sub V, and the 0 vector from W as 0 sub W. Let's take our linear transformation from earlier for an example. We have the mapping from R3 to R2 given by L of V equals V1, V2 minus V3. To find the kernel, we want to find which vectors in R3 give 0W under this transformation. This just ends up boiling down to solving the equation L of V equals 0W for possible values of V1, V2, and V3. In this case, that will be as follows. V1, V2 minus V3 equals 0, 0. This reduces to a simple pair of equations. V1 equals 0 and V2 minus V3 equals 0. Solving these gives us V1 equals 0 and V2 equals V3. This means that any vector from R3 of the form 0, C, C, where the first element is 0 and the second and third are equal to one another, will give the 0 vector in W when transformed. The set of vectors of this form is our kernel. Before we move on, it's worth noting that the kernel of L is a subspace of V, and for any subspace S of V, the image of S is a subspace of W. So any vectors from a kernel or image immediately follow all the properties of subspaces we already learned. Now with these definitions understood, let's check comprehension. Me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.
Okay. With this, we are done with 4.1. So in our next class, after the Thanksgiving break, we're going to do 4.2, matrix representation of linear transformation. So study smart for the Monday's exam and then enjoy your Thanksgiving. Okay, don't be late on Monday and I'll be here earlier. So if you have any question, I can help you with them. Inshallah. No. Except Monday, Wednesday, every day I'm at Baruch.
Oh, every other day you have group?
Yeah,
Oh, okay.
but if you want.
Can I like email you some?